Okay, I got a question about working on end bells. This is off a little motor. It's the only end bell I had handy. Question was, because what happens is this area in here where the bearing goes gets worn out on these. And they wanted to know what size lathe they needed to be able to sleeve these. So there's quite a little discussion on this that needs to be. And part of that is sometimes with a cast iron one, brazing them up works better than sleeving them. Without having the worn out end bell here to look at, we don't know. So we're going to add section on brazing, which can also end up going again in other brazing description, but we'll put that in with this in case you were working with a cast iron one. And the reason why you would do that with a cast iron one normally is the end bell is real thin on the sides here. There's a point where you're not going to, and if it was an aluminum one, which this one is, you're going to weld it up instead of just boring it out. Your smaller, cheaper motors like this one may have a high percentage of zinc in the aluminum, in which case it's not really aluminum, it's more what you'd call pot metal, and it does not weld well, in which case you definitely would be wanting to sleeve it. Now, this one here, you see this little wave washer. This little wave washer is in here to keep the bearing from just wandering back and forth. But they also don't give it a definite position for that bearing because the rotor, as it's working, it expands. The shaft gets longer, and this bearing needs to be able to slide and move. So that's where you have a little bit of trouble with these if they're sleeved with steel a lot of times. When you sleeve it with steel, the steel, if you get it a little bit too tight, it'll bind on there and you will ruin the bearings right away because it won't be able to slide. It will stick. The better materials, of course, if it's an aluminum end bell, you sleeve it with aluminum. If it's cast iron, you sleeve it with cast iron. It's good on an end bell if you are repairing it with a sleeve to pin it. Put a little pin through it. Common way to put a pin through it that works and you don't have to worry about the pin coming out is you drill and tap a hole through your sleeve after you put it in, put a screw in there, and then cut off with a burr or a die grinder the head of the screw. Just get rid of it. But we're back to the idea of what size machine do we want? Well, obviously, it's got to be larger than your bell. And we'll go look up some frame sizes for motors. They said 100-horse motor, but there's a lot of difference in a 100-horse motor. It's not just a straight, if it is an older motor, it's going to be bigger, but they're probably not working on antique motors. They're most likely thinking current production motors, normal frame sizes. But again, it's going to be a lot bigger for a 600 RPM motor than it is for a 3600 RPM motor. The same horsepower, higher RPM, lower torque, it doesn't need to be as big to obtain that torque. So, also, when you're chucking this up, if we're chucking this up and going to work on it, in this case here, you definitely want a 4-jaw. Any of your end bells, there's nothing really smooth or easy to work with here. And you need to look at where you are dialing in on. You need it flat on this position right here. You'll also find that some end bells, this one here is closed end, so you have to bore and come to a stop. There's some of them that are through bored. They go all the way through, and there's a plug that goes on the end. You'll see that more common on bigger end bells. An alternate I'm going to throw out there as opposed to the lathe, and we'll look up the sizes here in a little bit. And Bert might cut out while I go find the book and look it up. But as an alternate is a milling machine. The reason I say a milling machine is a relatively small milling machine can come in here, bore this out, and you can have a big end bell out here. You have to center it again off of this. Now, getting this flat in this milling machine is a little bit of a problem as far as, because it needs to be flat off of this face here. So if it was one that went through, it wouldn't be a problem. We'd put this on blocks. The hole would be through. We would be square, just being squared with the table if we have our head dialed in. And then we'd come in, dial in the hole. We could bore this out. There's pretty much standard bearings that are used in motors today, ball bearings. There's a common series of them. So if you did this with a mill, you might decide to not even get a lathe, or you can at least get by with a smaller lathe. It's no longer essential that you have, because if you have an in-bill that's 18 inches across, and that might be a size from my memory thinking for a 100 horse motor. If it's 18 inches across, then you don't need a 20-inch lathe, you need a 30-inch lathe or so. This is a 20-inch lathe, but your jaws are going to be out past your end bell. So you have to be able to clear not just the end bell, but the chuck and the chuck jaws as they stick out. And you can't always, bigger end bell, they're going to be really rounded here. So they have a rounded corner there, so you can't just use the other side of the jaws. This one, it would work, but on a bigger one, you're going to be right on that radius and it won't grab it. So you have to have clearance for the whole jaw. So I'm really pushing towards, as far as for boring out the end bells, to go towards a milling machine. Now, another thing, let's say it's a closed one like this. We'll go back to our mill here for a second. Or we can walk over to our bigger lathe. This one's way bigger, but you could start doing bigger end bells on this one here if you wanted. Now, the advantage to the lathe is that we get to dial in on this surface here for flat, where we can move it in the forejaw, and dial in on the center. We get to do that all directly. If we're going back to the mill, a trick that you do many times is you'll grab your blocks. Come on, open up. Everybody should have lots of 1, 2, 3 blocks. Lots and lots of them. You might even have 2 of them that you leave in your toolbox that are precision, but you should have some that are sort of precision, piles of them, because they're cheap today. Okay, you set those, and you only want to clamp over the part that the block is setting on. So you'd have 3 clamping areas in here. This is setting true, figuring that this was a big hole through here, and you just bore that out. But let's say that it is a closed end and it's a big end bell and that doesn't work. Then what we're going to do is we're going to clamp it down like this at first, and we're going to come back and we're going to machine a few areas. You have to be a little careful, but you machine an area. It might be carefully machining where these bolts, draw bolts go through, might be over here, but machine some areas that are flat. Then turn this over and use those for your spacers, so that when we turn this over, we have that same flat alignment. Also, they're ball bearings. They're a little forgiving if we're not perfect. But with that technique, you're going to be within 5/1000ths of flat run out. It's fine. It will work good for an end bell on a motor, which again, it has to move. Now, the other thing, which is where we need a lathe or a good contractor to work with. What you're going to do here, we're going to work a piece of tubing. And let me see if I can find something here that's tubing. Nope. It's kind of small. Bigger stuff is out in the ice there. That's some tubing that's more in the size of what we'd use. So, we're going to put this in our lathe. We're not going to make it precision, but we're going to put it in our lathe so that there's no question about what we're talking about. And generally, when we're making this sleeve, we're going to use a longer piece of tubing. And that is one of the problems. It seems like it should be an inexpensive job to sleeve an end bell. It's not. It's not. And part of that is, like I was just saying, lining up on that little finicky surface, whether it's lining it up in a lathe or lining it up in a mill. Getting that all lined up, getting a good cut, doing this accurate. It's not as easy as it seems when you first just throw that out. And some of your motors don't have little wave washers either. Some of them have the ends more close to their position. They'll let them float a little bit. They might have snap ring grooves. And snap ring grooves can be another problem to cut in these, which is easy to do in a lathe. It's a little bit harder on a milling machine unless you have a facing head, which is a good thing to get if you're doing this with a mill, just to have one. You're going to find some places where you want to do a flat surface. They're more expensive, but they're worth getting. The big key and takeaway here is when we set up our tubing for this, you turn the outside and you bore the inside without moving it in the chuck so that you have consistent thickness. And what you do is you will set the outside so that you have a little bit of a press in your hole that you bored out. And then when you go to bore the inside, do your calculations and work with the thickness of the stock, because that will be what's a more accurate measurement than measuring the bore directly for what you want. The bore may move a little bit as far as the outside diameter. What's going to happen when you press this in lightly is the inside is going to shrink down. It won't be the size in the part that you're measuring. And you generally want to make it so that your bore is going to be slightly tighter than what you want it. Then you can, normally you're going to end up using a flapper wheel. A hone would be real nice, but again, you have that closed bore lots of times where you can't get in there. And so you get this close and you use a flapper wheel, or you get real good at it. If you're doing these every day, you're probably not going to have to hit it with a flapper wheel very often. You're going to have this thickness down to where that's what you want. As an alternate, what you could do is you could go to somebody as a contractor and have them make sleeves that are a little bit long, but they're the correct diameter for a given bearing, if there's ones that you are going to do over and over again. And they could kick these out relatively cheaply, some shop on it, but you're going to have to buy 100 or 1,000 of them to bring the price down. You're not going to get a good price from somebody making 5 or 10 of them. You're back to where you need an in-house, a person at a lathe. And that's a lot to store. It depends on how much of this you're going to do. There's a few things to think about. Sleeving it with steel, I'm really against that. I have done it. It's what customers have recommended before. I've seen motors I've torn apart where they were sleeved with steel and the bearing was just either running around all over in there or the bearing was quickly fried because it couldn't move. Where cast iron, aluminum, bronze, those work good. Those give you a bearing surface where it will slide a little bit and still have a slight friction. Ideal is going to be somewhere on a smaller bearing, a quarter, half a thousandths. Bigger bearing might be 1/1000th that it presses. A lot of new ones you look, they are metal to metal. There's nothing wrong with metal to metal. They do another trick in here too sometimes, which you're not going to get in the rebuild because you're not getting to design this, but it works really good where you have a bearing that slides back and forth, doesn't really have its own dedicated lubrication system for that function, but they'll make an area in here where it slides back and forth and then put an O-ring groove in it and put an O-ring in there just so there's a little bit of extra friction to not let the bearing at first get to spinning. So it's still, the O-ring will let it slide back and forth, but keeps it from trying to rotate. That initial where you have enough clearance that it can rotate. It doesn't want to rotate easy. We're hoping it doesn't. Once it starts rotating, even if the bearing's good, it'll eat out the housing again. Not sure if I'm answering everybody's questions, but that's kind of a rundown on it. Some thoughts. I thought I had more thoughts than that, but that's some thoughts on doing in-bells anyway. Let's go look up the motor sizes. And we figure it's going to depend on your chuck, but you're going to need at least an 8-inch more swing than whatever the bell size is if you're going to be turning the bells on a lathe. You guys can't see it, but it looks like Bert's falling asleep back behind the camera. And that's to be expected. Him and his wife are close to having more trike motors at home soon. So they're doing stuff. Okay. This is a good book here. Fluid Power Data book. I think it was Womack Engineering, but we'll see in here. Yeah, Womack Educational Publications. There's a lot of good information in here, but I always forget which section is which. Small enough you think you're going to just have it. Electrical motor data. That would be 51, which could be the electrical one, or it could be the frame sizes. Here's frame sizes on page 51. So, they're not telling me which frame is which horsepower now. Seems like they used to have that, I thought. Quick reference chart. Okay, they do. It's on the next page over. So, we're in, no, NO, frame dimensions. Okay, no, they're telling us about the frames of the motors. We still don't know the horsepower versus frame. So I'm going to do a quick eNet search and see what a frame for an 1800 RPM 100 horse motor would be, because that's going to be the most common. It doesn't mean you're going to do all motors, but you're going to get the most common ones. And since they put that 100 horse as the upper end, they probably are not looking to do 100 horse in all kinds of varieties. And you call it 1800, but it's not really 1800. It looks like a 405T is the common one that people are coming back with real quick. So 405. Number frames prior to 1953. .405U, and we have got a 2F. Let's see, we're looking for BD is basically the diameter, but it's going to be a little bit more because we have the mounting feet. F. Oh, that's just length. That's not important to me. Oh, if we were on a C face, C is the length. P is a good one. We got P. P is good. Okay, P. 405. Okay, so we're looking at 20 and an 8 for our, between the mounting of the conduit connection and the other side of the motor. That's going to pretty much be what we're looking at. We're looking at 20 and an 8. So if we've got, say, 20-inch and we need another 8-inch, you're going to want a 28-inch lathe if you're going to want to do those. And you're going to want a chuck on there that's going to be at least a 26-inch chuck. 24, you'd have 2 inches over. You could, 24 may work, but you want a good sized chuck, so you've got something for that end bell to go against, and you're going to be having your jaws go out there. Now, you could do it another way. You could use a smaller lathe, and you could, not a lot smaller. It's got to turn the 20 inches, you know. So you're looking at a 24-inch lathe as a minimum. So 24-inch lathe, you could have special jaws made or make special jaws that offset and came around. So you don't have to have the standard jaws to where you're needing a 28 or a 30-inch lathe. Also, a 28 or 30-inch lathe is going to be really cumbersome to run for doing your smaller motors. So at that point, you might want to get two different lathes. And what I would suggest if we got back to this and we did this with a vertical mill where you were milling out the pockets and using a lathe just to make the sleeves, I would say you're going to do okay with the sleeves with any of the industrial lathes, something that is three-phase, over 5 horsepower, 14-inch minimum swing on up to 20-inch. I wouldn't really want to go over 20-inch for making the sleeves because they become more cumbersome, harder to work on the sleeves. And I don't want to go under 14-inch because the ones under 14-inch, with one exception in history, are normally pretty junky lathes. The one exception is a thing called a Monarch 10EE. And if you could get a rebuilt Monarch 10EE, that would be great for doing your sleeves, but one that's truly rebuilt is going to cost you way more than a brand new Taiwan lathe. One that's truly rebuilt is $50,000, possibly 120 if you're going for one rebuilt by Monarch themselves. But they're money. They're neat lathes. I've got two of them. Again, not enough room in the shop. I don't get to use them no more. They are creased down, outside, covered over, super tarped. I sad for them too. Um, can't have everything in the shop. Shop's too small. It's the same size. My shop is the same size as your shop. It's too small. I got 5,000 square foot, not real big by industrial standards for sure. Definitely fair size by homeowner type standards. It would be a fair size shop, but no, it's too small. It also costs a lot to heat if we had a bigger one. I've ranted about that before. So that's, yeah, my real choice would be to get a, and I wouldn't get a Series 1 Bridgeport. I would probably, if money's not an option, I think you're probably looking in the $50,000 range. I would get a Sharp 10 or 11 by 54, whatever they've got in that range of a turret milling machine. If money's an option, I'd start going with a Taiwan comparable. It's going to be around 15,000. Again, I'd go with the bigger ones. I wouldn't go with a new Bridgeport Series 1. While they're nice machines, and I think you can get one for under 20 yet, they're not as big. That extra size of the table for what you're doing is going to be very nice. Maybe not totally essential, but nice. So I would go with a little bit bigger vertical mill. I would then ideally go with, I'd probably say a 16 or 18-inch lathe. Well, I said, you know, that a 14 will work. That's the minimum size. And I'd rather see you go with a 16 or 18 because those are higher RPM lathes generally than the 20, a little bit easier tooling. You're going to want, if you're using the smaller sizes, and probably even if you get up in the 20-inch lathe, I use the 20-inch lathes with a D-series Aloris tool posts. They're a little big and cumbersome for a 20-inch, but they're a lot more rigid than the other ones. For what you're doing, the C series is going to be just fine. The CAs, you want the taper lock series tool holder. You're going to find that that's really, and tooling is going to be a lot of it on this. It's going to be the same thing on your mill. You're going to want a adjustable boring head. You're going to want to get lots of boring tools. You ideally would want one that has facing on it. I tend to gravitate towards the Narex. I've had real good results with the Narex kits. It could be good to have both so that you can leave your Narex there and keep it in good shape and then get a less expensive non-facing head so you've got both styles. If they give you a choice on the machine, I'd probably go ahead and go with the 30 or 40 taper spindle over the R8. The tooling is not as common, a little harder to get, but it's just a lot better connection on the machine. Can't really say everything as to what you're going to need. You're going to need somebody that's really versed in what they're doing to run this machinery and make value out of it for you too. you can have people that'll mess things up in a hurry and make it all not worthwhile. I'm sure you probably have some other questions. You can bounce them back at me. Send it at my actual, well, you caught my old email. My other email, if you go to the About link on YouTube, you can get my email that I normally use now. The old one that you got off of my website, I do still use that one too, but not as much.